Okay, so now I'm going to talk about non-homogeneous second order linear equation. Okay, so we have already done non-homogeneous first order linear equations. If you recall, those are of the form, this form, right? And then the solution to these is given by the solution to such an equation is given by c e raised to power minus I plus e raised to power minus I q e raised to power I dx. Okay, so remember that this was a solution to the corresponding homogeneous equation. This part is the solution that you get when you set q is equal to 0, and this is known as the particular solution or the particular integral. Okay, so this is the solution. Yp is the solution to the equation when q is non-zero. Okay, and this yc is the complementary solution or the solution that corresponds to the homogeneous equation. Okay, so what happens when you have a second order linear equation? Okay, so essentially you're looking for something like this. Okay, so you have, for example, d of x and dy by dx plus, say, q of x, y is equal to r of x, where r of x is of course now non-zero because you're dealing with a non-homogeneous equation. Okay, so first of all, remember that I can write this as some linear operator x and y is equal to r of x. Okay, fine. Just for consistency with the notation followed in Boas, let me call this f of x. Okay, so that you're not confused when you read the book. So this is f of x. Okay, fine. So the idea behind solving this non-homogeneous equation is to first of all solve the corresponding homogeneous equation. Okay, and then find a solution, one solution to this non-homogeneous equation. Remember, you have a whole family of solution corresponding to the homogeneous solution. So you have two constants in the when you solve the homogeneous equation. Of course, those two constants can have particular values if you specify the initial conditions or the boundary conditions. Okay, but the particular integral, the particular solution, does not contain a constant. Notice that in the first order case, okay, there is no constant over here. The constant is over here. Okay, so the idea is that you first of all find the solution to the homogeneous equation, okay, and then add to it a solution of the non-homogeneous solution, and the sum of the complementary solution, okay, complementary solution and the particular solution is your most general solution to your second order linear equation. Okay, fine. Let's see now why does that work. It all relies on the linearity of this operator, the fact that this is a linear operator. Okay, so by definition I know that this linear operator, when x and yc, okay, yc, remember, is the solution of the differential equation when this thing is 0. Okay, so I know that this thing x and yc gives me 0. Okay, and by definition the linear differential operator x on yp, okay, to give me f of x, because I said that yp is any function that satisfies this differential equation. Okay, let me just be explicit and write down that L is given by the double derivative plus p of x. Okay, I haven't really specified what p and q are. Okay, they're just any arbitrary functions of x. They can be constants, of course. Okay, so this is p of x and your derivative plus, that's your linear operator. Okay, so these two equations just come from the definitions of yc and yp. Now if I act this linear operator on the sum of yc and yp, okay, by the definition of linearity I get that this thing is equal to yc lyc plus lyp, okay, and this thing is then equal to 0 plus f of x, okay, right, using these two equations. And so this is equal to f of x. In other words, you have obtained that lyc plus yp is equal to f of x, and so yc plus yp is the solution, the most general solution to your second order linear differential equation. Actually, you can generalize this to higher order linear differential equations as well, okay, but the differential operator has to be linear, okay, right. So the most general solution, so what we have found is that the most general solution is given by y is equal to yc plus yp. That's exactly what you found in the case of first order equations as well. So this is yc plus yp, okay, right. And this is good to know, okay, because we know how to solve for we know how to solve for yc, okay, so that's good. So then all you need to do is to figure out methods to solve for yp, okay. Okay, so now we have to discuss how to find out the particular integral for different cases. Okay, so there are techniques in general for second order linear differential equations that allow you to do that, okay, but those techniques can be a bit long-winded to apply, okay, so it takes the working can become a little bit messy, okay, and most of the time those techniques are a little bit overkill, okay, right. So the good thing about finding out the particular integral is that in many cases you can kind of guess the solution, okay, and then you can check the solution, okay, and if your solution is slightly off, if your guess is slightly off, you can very quickly learn how to modify your guess such that it becomes actually the particular integral, okay, right. So let me give you an example of that, okay. So for the rest of this session, essentially I'll be restricting myself to second order differential equations with these functions p and q being constants, okay. These are of course then by and large the equations that we have dealt with until now, okay. So second order linear differential equations with constant coefficients. This f of x on the other hand need not be a constant, okay, right. So the non-homogeneous term is not a constant, but the coefficients appearing in your linear operator are constants, okay. That's the assumption I'm making for now, okay. The next lecture essentially will deal with the case when the coefficients are also functions of x, okay, and those equations are much more difficult to solve, okay, right. So the first case that I'll deal with is that f of x also is a constant, okay. So let's just call that constant c, okay. So how do you find this out? So then suppose that the differential equation I can then write as y plus a1 y prime plus a naught is equal to c, or you can of course write this as d square plus a1 d plus a naught acting on y, or there is y of course over here, okay. So you can very easily guess the solution, okay. The solution is simply c over a naught, okay. Why? Because this is a constant, because c is a constant and a naught is a constant, so the double derivative is going to be 0. This thing is going to be 0 as well, and y of course is c over a naught, so when you plug this thing over here you will be left with c, okay. So the most general solution to this differential equation would be, how do you obtain that? The most general solution would be, this is, remember, simply yp actually, okay. So first of all you find yc. So to find yc we write, okay, d square plus a1d plus a naught y is equal to 0, okay. So you first of all find out the complementary solution, okay, by setting the homogeneity equal to by considering the homogeneous equation, okay. So you treat this as an algebraic equation, find out the roots, then the complementary solution is essentially e raised to power lambda 1 x plus e raised to power lambda 2x, a superposition of those two where lambda 1 and lambda 2 are roots of this equation, okay. So yc is simply c1 e raised to power lambda 1 x plus c2 e raised to power lambda 2x. Okay, and the total solution is then yc plus yp, where this thing is simply c over a naught. Okay, that's your most general solution to this non-homogeneous second order linear equation. Okay, right? Okay, but that's a very boring case. Okay, in general, f of x is going to be a function of x. One physical example just to motivate where that equation can come from. Again, you can consider a simple harmonic oscillator. Okay, and so you have some damping as well present. So the net force acting on it will be minus kx minus l dx by dt. Okay, and this and then this is the spring force, this is the damping resistive force proportional to the velocity of the block. But now you are on top of this also applying some kind of periodic force onto this block. Okay, so you are pushing this block periodically. Okay, so that is, and that of course push can be a function of time. Okay, so you have essentially over here you can write down minus f t, okay, is equal to m, just put this as plus. Okay, so you can take these to the other side, and then you have of course okay, this of course is now a non-homogeneous equation. Okay, so that's one physical context of course in which non-homogeneous equations can naturally arise. You see a very similar equation for RLC circuits, okay, in which some AC source is present as well, and they pop up all over the place. Right, so how do you solve this? You just have to find out the particular integral. Okay, so to find out the particular integral, what we first did is there's a systematic way of doing that. Okay, but most of the time since you know in physics we are as lazy as possible. Okay, once we have gained some experience with that systematic way, okay, you forget about that. Okay, and then you can usually guess the solution. Okay, and I'll show you how that works. Okay, but first let me give you how you can solve this equation. Okay, the second order, find out the particular integral of the second order linear differential equation with constant coefficients. Okay, in general. Okay, this equation, but with, where is it gone, this equation, but with p and q constant. Okay, so when p and q are constants, of course I can factorize the linear operator. So I can write d minus a, d minus b. A and b are the roots of the corresponding algebraic equation, and this is equal to f of x. That's my non-homogeneous equation. Okay, so the first step is that you say that this is u. So you defined u as d minus b times y. Okay, the idea behind this is that you essentially reduce your second order differential equation to two first order differential equations. Okay, and then you have that you can write u is equal to f of x, right? Okay, and from here you can write that this implies that du by dx of course minus au is equal to f of x, and you are happy to see this because this is the first order non-homogeneous equation and we know how to solve this. So first of all, this implies that the factor I will be given by integral of p dx, but here the integral of p dx is going to be minus a dx is equal to minus ax. Okay, so this means immediately that u is going to be some constant e raised to power minus I. Okay, that's going to give you e raised to power ax. Okay, plus e raised to power ax, and then integral of q, which is f of x, right? And then you are going to get e raised to power I. Okay, so that is going to give you e raised to power minus ax dx. Okay, so that's essentially what you have. Fine. Once you have this thing, right, once you have this thing, you can then substitute back over here. So you can substitute this thing over here, and then you have a first order linear differential equation for y, and then you solve that. Okay, and that in turn is going to give you eventually the complete solution for y. Okay, it's going to give you the complementary solution plus the particular integral as well. Okay, right. So let's see how does that work in practice. Okay, for an actual example of f of x. Okay, so let's say that you have essentially that f of x is equal to some constant multiplied by e raised to power cx. Okay, so you have over here essentially let's work it out. Okay, e raised to power cx. So using this solution, u is equal to c. Oh, let me use some other constant over here, c1. Okay, let me just call it c1. c1 e raised to power ax, right? Okay, fine. Plus right, e plus e raised to power ax. Then I'm going to have k e raised to power cx e raised to power minus ax dx. Okay, that's what I have. Okay, now I'm going to assume that c is not equal to a. Okay, we'll learn how to do that case later on. Okay, if c is equal to a, then of course you're going to simply get kx from this thing. Okay, but c is not equal to a. Okay, so you're going to get over here u is equal to c1 e raised to power ax plus c is not equal to a, so you're going to get as constant k divided by c minus a. That is some new constant which I call k prime. Okay, so you're then left with e raised to power ax, and you have over here of course after the integral the exponential remains the same. Okay, so we are going to get over here e raised to power c minus a x, right? Okay, fine. That's essentially what we have. Okay, you might worry that of course there will be some new constant from here, the constant of integral once you do the antiderivative, constant of integration once you do the antiderivative. Fine, we can put that in as well if you want. Okay, and that is then going to give me c1 e raised to power ax plus k prime e raised to power cx plus k prime c2 e raised to power ax. Okay, this and this I can combine and write down a new constant if you want, which I call c1 prime e raised to power ax plus k prime e raised to power cx. Okay, but this is only u. Okay, so you see it's a bit tedious. Okay, it's much longer than you just quickly guessing the solution. Okay, so u is equal to of course d minus b times y. So you'll be writing that dy by dx minus by is equal to c1 prime e raised to power ax plus k prime e raised to power cx, right? And then you'll be writing, okay, that u is equal to y is equal to y is equal to e raised to power bx. Okay, some new constant, let's call it c3. Okay, e raised to power bx okay, plus integral of, let's use the first order linear homogeneous equations expression. Okay, e raised to power minus bx, and then you have q over here, c1 prime e raised to power ax plus k prime e raised to power cx. Okay, dx. Okay, right? So this is going to be e raised to power bx c3 plus, oops, there's also e raised to power bx outside. Okay, So this thing is then the first time you're going to integrate, you're going to get a constant. Again, now I'm assuming also that a is also not equal to b. Okay, so as in a and b and c are different. Okay, all three from each other. Okay, so you can then define a new constant c1 double prime when you do this integral, because this is going to give you c1 prime divided by a minus b. Okay, which I call a c1 double prime, and then e raised to power a minus b is going to be left over, but that is going to be multiplied by e raised to power bx to give you e raised to power ax. Okay, right, fine. And then you have plus over here, you have essentially, when you do this integral, you are going to get e raised to power c minus b x. Okay, and then this k prime is going to be redefined to k double prime, say, and then e raised to power c minus b x, and then e raised to power bx. Okay, and plus you will also get a constant of integration. Okay, so you are going to get e raised to power bx c4. Okay, so these two you can combine into a single term. Okay, which I call as, well, you just have to redefine constants again and again. Okay, right, and you also have c1 double prime e raised to power ax plus k double prime e raised to power cx. Okay, fine, that was a lot of work, huh? Okay, so to recap, okay, so let me just redefine my constant so that I can just, the solution is of this form, that you have some constant. Okay, c1 e raised to power ax plus c2 e raised to power bx plus capital C e raised to power small c times x. Okay, that's the form of your solution. Okay. If you notice, this is simply the solution of your homogeneous equation. Remember, you were solving d minus a, d minus b is equal to f of x. If you consider the corresponding homogeneous equation, this is 0, and you already know the form of the solution. That's just going to be e raised to power ax multiplied by c1 plus c2 multiplied by e raised to power bx. Okay, this shows you, remember that f of x you are assuming to be of the form k e raised to power cx. This just means that you can already assume, to find out the particular integral, you just assume that the solution of this equation, that the particular integral of this equation, non-homogeneous equation, is of the form some constant which you need to find, multiplied by e raised to power cx, where this c, remember, is the same as that c. Okay, and remember, small c can be complex as well. Okay, which immediately leads to you being able to deal with sinusoidal driving over here. Okay, so let's see how that works out for some actual examples. So for example, suppose you have essentially you have over here, let me just, d minus 1 d plus 5 is equal to 7 e raised to power 2x. Okay, okay, so but before you start blindly trying out your guess, okay, check that the conditions are met. Your conditions were such that, first of all, a is, let me just, a is not equal to b. Okay, and c is also not equal to a. Okay, right, fine. So what happens then? So you also have over here, oh, by the way, I forgot, when you were doing this step, right, when you were integrating this thing multiplied by this thing, when you were integrating this, you were also assuming that c is not equal to b. Okay, so in other words, this just means that a and b and c are all different. Okay, so you have to solve this. Okay, so it's obvious from this equation, so there's a y over here, it's obvious from this equation that a is equal to 1 and b is equal to minus 5 and c is equal to 2. So this condition is met. Okay, and then you can immediately, first of all, you write down the complementary solution. The complementary solution is, of course, that. The particular, to find out the particular integral, you say, okay, I'll assume that my particular integral is of the form capital C, which I've defined. Okay, so this method is known as a method of undetermined coefficients. Okay, because you leave some coefficients, okay, in your guess whose values you can determine by plugging your guess into your differential equation. Okay, so yp is equal to e raised to power small cx, so that is your guess. Okay, and by plugging this guess into your differential equation, you can figure out what the value of this capital C is. So your differential equation is d square plus 5d minus d plus 4d minus 5 x and y, and this is equal to 7e raised to power 2x. Okay, so d square plus 4d minus 5. Now I plug in my guess, c e raised to power 2x. Okay, let's work this out. So c of course goes outside when first d square x on this thing. Okay, c goes outside when d square x on e raised to power 2x, two factors of 2 are brought down, so that gives you a factor of 4, and you have e raised to power 2x as it is. Okay, and then you have plus 4c when you are acting this on that. Okay, so 4c can be brought out, and dx on e raised to power 2x to bring down another factor of 2, and you have e raised to power 2x as it is. And then you have minus 5c e raised to power 2x, and this of course I can write as 4c plus 8c minus 5c e raised to power 2x, and this is 12 minus 5, which is 7 c e raised to power 2x, and this of course has to be equal to 7 e raised to power 2x, from which it is clear that c must be equal to 1. So your guess should be, so your particular integral simply now is e raised to power 2x. Okay, and so the most general solution to your second order linear differential equation is simply c1 e raised to power over here I should be writing e raised to power x. Okay, c1 e raised to power x plus c2 e raised to power minus 5x plus e raised to power 2x. Okay, so that's what I have. Notice one very important thing. Okay, which leads up to the next points that I'll be making. Okay, your particular integral, the form of your particular integral, this thing is linearly independent from these. Okay, let's check this. Okay, so you have two functions, e raised to power x and e raised to power 2x. Okay, so you have this function and this function. Let's calculate the Wronskian of these two functions. You'll get e raised to power x, e raised to power 2x, then derivatives of these functions, and you have got 2 e raised to power 2x, and this is going to give you 2 e raised to power 3x minus e raised to power 3x, which is going to give you e raised to power 3x. So this is non-zero, so they are linearly independent. Okay, so that's why our guess works. Okay, if for example c is equal to a, then you would be guessing that the particular form of the integral is already of the same form as part of the complementary solution. Okay, but that is not going to work. Okay, because the complementary solution already contains that part. The particular integral has to give you information beyond the complementary solution. Okay, and this will become clear as we work a few more examples. Okay, just to make this point clear, suppose you have found the complementary solution. Okay, right, or even one part of the complementary solution. So as you remember, the complementary solution consists of two parts. You add the two and you get the full complementary solution. But suppose you have found only part of it. Okay, you know that this has to be true. Okay, because the complementary solution is the solution to your homogeneous equation. Okay, then the point is that yp cannot be a multiple of yc. It cannot be a multiple of any part of the complementary function. Okay, why? Because any part of the complementary solution of course satisfies this equation. Okay, so for example in this in this case, if this operator x on e raised to power x, this thing, you are guaranteed to get 0. If this operator x on e raised to power minus 5x, you are again guaranteed to get 0. Okay, that's what I mean by different parts of the complementary solution, okay, or complementary function. So yp cannot be a multiple of yc. Okay, so your guess better not be a multiple of yc, because that is guaranteed to fail. Okay, because essentially if yp is a multiple of yc, okay, so if you guess that yp is that, okay, so if your guess, for example, in this condition would be capital C multiplied by e raised to power x, that is never going to work. Okay, why is that never going to work? Because remember, the actual equation that you're trying to solve is to find the particular integral. You need to satisfy this equation, right? Okay, that's the equation that the particular integral needs to solve. But now you substitute your guess, and you get on the left hand side this. C is a constant, L is a linear operator, so you can bring C outside, and you're left with L acts on by C. But this, by the definition of yc, is 0. So the whole thing is 0. It's never going to be equal to f of x. Okay. So that's what I meant, okay, that yp better not be a multiple of yc, and that is why actually these conditions are important. These guarantee that your guess is not a multiple of these functions appearing in your complementary function. Okay, that's exactly why I said C is not equal to B. That guarantees that your guess is going to be linearly independent. On the other hand, if C was equal to A, okay, so it turns out that you can find roots such that C is exactly of the same, that C is equal to A, okay, then of course your guess is going to fail, okay, because then you just you better make a different guess, okay, right? Let's see an example of that. Suppose I have this differential equation, d square, right, okay, plus d minus 2y is equal to e raised to power x. Okay, so okay, you are very happy. You say, okay, I know how to do this. You first of all treat this as an algebraic equation. You find out the roots. The roots turn out to be, you factorize this as d minus 1, d plus 2, right? D square plus 2d minus d minus 2, right? Okay, so the roots are a is equal to 1 and b is equal to minus 2. Now you're in trouble, right? So you see, this thing is exactly the same as this power, which is also 1, right? So in other words, you're going to write down that, okay, yc, you're still happy, you see, is equal to e raised to power x plus c2 e raised to power minus 2x, right? And then to find yp, you say, okay, I know this rule, I know the form of the guess that I have to make. C multiplied by e raised to power small c multiplied by x, and small c over here, remember, is 1, and then that is your guess. But that is never going to work, because remember, that's your problem. Okay, your guess is already contained in your complementary function. Okay. Now you can go back, if you are faced with such a scenario, you can go back all the way back when we were doing this stuff, okay, when we're playing around over here, okay, you can go back, of course, and you have to be careful, okay, over here, that you're not making this assumption. So for example, if c is equal to a, then essentially, for example, over here, let's see where that comes in, that c is equal to a, okay, c is equal to a, that probably that's where this comes in, okay. So you don't divide over here. This, when c is equal to a, this immediately goes to 1, okay. So you are left with kx over here, rather than some constant multiplied by e raised to power cx, right? You're left with some constant k multiplied by x multiplied by e raised to power ax, okay. Okay, and a, of course, is equal to c. Okay, so that's the difference, okay. And you could have guessed that from what we did before when we were solving homogeneous equations. There we found that if you have a double root, so you have something like this, then remember the solution was c1 e raised to power ax plus c2x e raised to power ax. Okay, since these two are not linearly independent. Okay, so in other words, because you want your yp to be independent from yc, your guess should no longer be this thing. Your guess rather should be c, capital C, whose value you have to find by plugging in yp into the differential equation such that it is satisfied, multiplied by x e raised to power x. Okay, you can justify this guess rigorously as before by going back all the way over here. Okay, right, all the way over here, but okay, but it works. Okay, if you're not satisfied, you can do the working yourself. Okay, but it's just long, boring and tedious. Okay, so let's work it out. Okay, let's see what this value of c comes out to be for our differential equation, this differential equation. So d square plus d minus 2y is equal to e raised to power x, and I'm trying to find out the particular integral. Okay, so my guess is this thing. Okay, so let's just plug this in. So d square plus d minus 2 yp, let's work this out. Okay, so first of all, let me do the working over here. D acting on yp, that's slightly more complicated because you have to apply the product rule. C goes outside, x goes outside, this is differentiated. Okay, and plus this goes outside and x is differentiated, you get 1, so you get c e raised to power x, right, and you get x plus 1. Then d square yp, you differentiate this once more. Okay, so c goes outside, this goes outside, you differentiate this thing, but that gives you 1, plus c goes outside, this goes outside, and differentiate e raised to power x, you get e raised to power x. So you're left with c e raised to power x, x plus 1. Okay, right, so it turns out that taking two derivatives, you get exactly the same thing. Okay, so you get this thing is c e raised to power x, x plus 1, plus d acting on yp, that gives you exactly the same thing, so you get a factor of 2 minus 2 2c x e raised to power x, right, and this has to be equal to, of course, e raised to power x. Oops. Right, so this has to be equal to e raised to power x, and then just expanding this out, you get 2c e raised to power x, x plus 2c e raised to power x minus 2c x e raised to power x has to be equal to e raised to power x. So this cancels that, and we immediately find that c must be equal to half. So in other words, the particular solution is simply equal to half multiplied by x e raised to power x. Okay, so with this in mind, let's do another case. Okay, I just explained it. So suppose that over here, right, we were assuming, let's see, we were getting a repeated root, right? So essentially, not exactly a repeated root, but essentially what you were finding was that a is equal to where is it, right, you're finding that a is equal to 1 and b is equal to minus 2. Okay, so on the other hand, c is also equal to 1. Okay, so you're finding that a is equal to c. Okay, so what happens if a is equal to b is equal to c? Okay, you can go back to the U business. Okay, first reducing the second order differential equation to two first order differential equation, then solving it. But it's easy to guess that in this case, okay, since this case we already have covered the functions e raised to power x and x multiplied by e raised to power x. Okay, if this was the case that b is also equal to c, then you also need, of course, that your guess should be that of this form. Okay, that should be the form of your guess. Okay, because yc, the complementary solution, already contains x multiplied by e raised to power cx. Okay, now I want to actually consider sinusoidal driving into homogeneous time. Okay. What do I mean by that? Okay, so physical example, consider again a harmonic oscillator. So you have essentially, block attached over here, and we already saw that the equation of motion for this thing can be written as, so y is your displacement of your block, using Newton's second law. This thing is equal to minus ky, okay, by Hooke's law. Okay, and you also have this as a damping term. Okay, and you can also add in some external force, okay, which is time dependent. Okay, this essentially is the force with which you are periodically pushing the block. Okay, so this is a function of time, right? And then you can rearrange this so to get plus L dy by dt plus ky is equal to f of t. Okay, and then you can divide throughout by m, and you can define as before 2b as L over m and omega naught square as k over m, and that will give you this thing. Okay, and of course over here I'll have essentially let's say we'll have f of t over m. Okay, right? Okay, and this I can write as, so assuming that the force is sinusoidal, so this thing will be f sine of omega t divided by m, right? And this thing I can call as, let's call it capital A sine of omega t. I'm calling it capital A so that it reminds me of acceleration. Remember, the dimensions of this thing are those of acceleration. Okay, so that's essentially the differential equation that I need to solve. I need to solve for y. Okay, so let me just write it out. Plus omega naught square y is equal to capital A sine omega t. Okay. Okay, so I'll be doing the underdamped case. So as in damping is present, but it's not so great that it actually overwhelms the solutions. Okay, so essentially B is quite small. Okay, so by and large the block oscillates. Okay, but eventually if there was no driving, the oscillations would die out eventually. Okay, but now there is driving present. Okay, so we need to figure out what happens in the presence of driving. Okay, and the first thing to do that, of course, is that we need to solve this differential equation, and I already know the form of the solution. So y will be equal to yc plus yp, and I already know the form of this thing. Okay, so we already discussed that this is these are essentially this is essentially a damped sinusoidal solution. Okay, and you can see that we did this in my previous set of videos. Okay, so our emphasis over here on the hand will be on finding the yp. Okay, so to find yp, I won't directly again my strategy would be that instead of actually going back and doing this by brute force, I'll try to guess the solution. Okay, and you can kind of guess the solution. There's a very neat strategy to do this. Okay, and the strategy is that instead of solving this differential equation, you solve a related differential equation. What you solve is essentially that you promote y to being complex in a way. Okay, so you write the differential equation in terms of capital Y. Okay, and I'll explain what capital Y is. Okay, and this is equal to, you said that equal to e raised to power I omega t. Okay, which looks strange. Okay, that the sign has disappeared, but remember the sign is trapped inside the exponential. The trick now, okay, is that by writing this, let me just write it again. dy by dt plus is that I define my small y, my original, the small y, remember, is the actual physical displacement of the block, as the imaginary part of capital Y. Okay, right, and also remember that the imaginary part of the sum of two complex numbers or the difference of two complex numbers is given by the sum of the individual imaginary parts or the difference of the individual imaginary parts, okay, as the case may be. Okay, fine. Then it is clear that imaginary part of dy by dt, okay, will be equal to, if you go to your definition, imaginary part of limit delta t approaches 0 of yt plus delta t minus yt over delta t, right? And this limit, of course, you can pull outside. This imaginary part sees this thing, okay. Delta t, of course, is also pulled outside. Well, not that far, sorry. Okay, delta t you can pull over here, okay. This imaginary part sees this thing in the square brackets, and then you can use this property to write this as this, that this numerator is the difference of the individual imaginary parts, okay. And the individual difference of the individual imaginary parts by this definition will just be equal to, so this is equal to limit of y t plus delta t minus that, and this of course is dy by dt. And by exactly the same logic, imaginary part of d2y, capital Y by dt2 is the double derivative of the actual physical displacement, okay. So in other words, if I consider this equation and take the imaginary part on both sides, I'll end up with, by choosing these properties that I've just derived, I'll end up with, you can just read it off. You'll have double derivative of small y plus 2b multiplied by single derivative of small y plus omega naught square multiplied by small y is equal to a multiplied by sine of omega t, which is exactly your original equation, this one, right? But this equation is easy to solve for capital Y, and once I have capital Y, I know how to find small y. I'll just take the imaginary part of capital Y, okay. Why is this equation easy to solve for capital Y? Because the driving term is of exponential form, and I know how to deal with such a form, okay, because I know how to deal with the non-homogeneous term being of this form. C, remember, can be complex, okay, and here the role of k is being played by capital A, and c is simply I omega. Of course, the role of x over here is being played by t, okay. Okay, so the differential equation we need to solve is, this one. Square y is equal to a e raised by omega t. I'll assume underdamped solutions for the complementary function, where in other words I can write this equation as d square plus 2b d plus omega naught square acting on y is equal to a e raised to power I omega t. I first look at the homogeneous version of this thing, and then I find out the roots of the algebraic expression corresponding to this. I remember in the underdamped case I got two different roots for this, okay. The roots had the imaginary part and real part, the real part corresponding to damping, the imaginary part corresponding to oscillatory behavior, okay. But the main point is that you have both real part and imaginary part for underdamped solutions, okay, for roots of this, the algebraic expression corresponding to this equation, okay. On the other hand, over here you have a purely imaginary number, okay. So remember, this corresponds to C, okay. The roots over here correspond to A and B in our usual notation, okay. Don't confuse this B with that B, okay. This denotes, this is essentially damping, okay. This B denotes the root, okay, right. So anyway, we are dealing with the case over here where these three are different, okay. So to find I don't write down the complementary function because the total solution is the sum of these two. I have already found out this before, okay, in the previous set of videos, okay. So I need to find this out. To find this out, of course, since A is not equal to B is not equal to C, I can simply guess that capital Y, be proper over here, I should be writing capital Y is equal to YC plus YP. Okay, so okay, right, so I've already found this, and I need to find out this. Okay, right, because finding out this thing amounts to solving this differential equation. Okay, and I've already done this in the previous set of videos. Okay, so to find YP, I assume solutions of the form this thing, because I'm dealing with this case. Okay, and I just substitute this back into the differential equation, and I work out what C should be. Okay, so I have over here d square, I have d square plus 2bd plus omega naught square c e raised to power I omega t. Okay, right, and this thing, let's just work this out what this gives you. Okay, so remember that let me just work it out over here. So dx on yp gives you I omega c e raised to power I omega t. D square x on yp to give you another factor of I omega, which gives you minus omega square c e raised to power I omega t. Okay, right, so this whole thing becomes over here, this whole thing becomes equal to what it is, becomes equal to minus omega square c e raised to power I omega t plus 2b I omega c e raised to power I omega t plus omega naught square c e raised to power I omega t, and this whole thing of course has to be equal to a times e raised to power I omega t. Okay, so since this has to hold true for all times t, I can just remove these exponentials. Okay, and I can just solve for c. So c from here, it comes out to be a divided by omega naught square minus omega square plus 2 I b omega. Okay, right, fine. Okay, over here, remember, when I find out from this thing, I need to find small y. Okay, to find small y, I need to take the imaginary part of capital Y. Okay, otherwise I'll be taking the imaginary part essentially of, I have to consider the imaginary part of the particular solution. So actually I'm not really interested in capital YP, I'm more interested in the imaginary part of capital YP. So in other words, I have to take the imaginary part of this thing. To take the imaginary part of this thing, it will be convenient if I can write this complex number C in polar form. Okay, right, because then finding out the imaginary part is straightforward. Okay, so first of all, to find out the polar form, of course I need to first find out the magnitude of C. Okay, so magnitude of C is given by, okay, you have A as it is. Okay, and then you need to find out, so if you have a complex number like that, the magnitude of Z is given by magnitude of Z1 divided by magnitude of Z2. Remember, A is real, so the magnitude of A is simply A. Okay, the magnitude of this thing in the denominator, of course, is more complicated. That is given by omega naught square minus omega square whole square plus 4 B square omega square. That's what you have for the magnitude of C. Okay, right, okay, I can then also express C in the form of, I want to express it in this form. Okay, it's convenient to write this as e raised to power minus I phi rather than e raised to power plus I phi, as will be obvious when we do the working. Okay, but to find out this angle over here, I need to find out first of all the real part and imaginary part of C. Okay, right, and so let's do that. Okay, so C is given by A over omega naught square minus omega square plus 2 b omega. So I can write this as A omega naught square minus omega square minus 2 b omega, right? This minus is essentially because is essentially why I put this minus sign over here, okay, with the angle. So anyway, so you have omega naught square. You have to be a bit careful when you do this calculation. Plus 2ib omega, right? And then you have omega naught square minus omega square minus 2ib omega. Okay. And this whole thing, of course, is a omega naught square minus omega square minus 2ib omega, right, divided by omega naught square minus omega square whole square, okay, and then you have plus 4b square omega square. That's what you have, okay, right? So the real part of C is given by a omega naught square minus omega square divided by omega naught square minus omega square whole square plus 4b square omega square. The imaginary part of C is given by minus 2a I b omega divided by omega naught square minus omega square whole square plus 4b square omega square, right? Fine. So essentially, if I draw this triangle over here, so this is phi, right? And you have over here 2a I b omega over right. This is this length, and this length on the other hand is a omega square minus omega square divided by omega naught square minus omega square whole square plus 4b square omega square. So the ratio of these two, okay, which of course is really the tangent of phi, okay, so I can write down the tangent of phi will be given by essentially the ratio of these two. So you'll get 2 so sorry, I should not be writing I over here, right? So I should get 2a b omega, okay. So when I take the ratio of the two, I'll have 2b omega over omega naught square minus omega square, okay, right? So this phi is essentially this phi, remember, okay? So that's what we have, right? So yp is equal to mod c. Let me just write down mod c is equal to a over, so this is equal to a over plus 4b square omega square, and you have e raised to the minus I phi, and we know how to find phi, okay, because we know how to find the real part of C and the imaginary part of C, and phi is just given by the ratio of those two, right? Okay. Okay, so then I need to find, so capital Y, the full solution to the differential equation given by yc plus yp, okay. This thing contains, because I'm using underdamping, okay, it contains some oscillatory solution, okay, and it also contains an exponentially damped part, okay, and we know how to find that, okay. So I wrote that down last time, but the important point is that this is also physically termed a transient solution. The reason being that this solution is effectively becomes zero at long times, okay, because of the exponentially decaying term. This solution, the solution that corresponds to driving, notice that if there is no driving, as in capital A is 0, yp is simply 0, of course. Okay, so this solution which corresponds to driving is what you are interested in. Okay, and then the solution to y due to driving, okay, is given by the imaginary part of capital Yp. Okay, and this is easy to write down because this is simply given by hang on. Right, because this is simply given by this thing over here. Okay, so capital Yp, let me just write it down first, is equal to mod c, which we know, e raised to minus I phi, and then e raised to power I omega t. Okay, right, so from here you immediately have that small yp will be equal to mod of c, which we know, and you have, when you take the imaginary part for these exponentials, you going to get omega t minus phi. So in other words, let me just write it down explicitly. Yp is given by a over square root of omega naught square minus omega square whole square plus 4b square omega square e raised to power, and that's mod c, and then you have sine of omega t minus phi. That's the solution of it. If you want a complete solution to the y, you just add to this the complementary function which we found last time. Okay. But if you're interested in the long time behavior, then you don't even need to do that, because you know that the complementary solution will go to 0 at long times. Okay, effectively 0. Okay, you can see from this solution, okay, yp. So yp first of all is also called the steady state solution. Okay, because once the transients die out, that's what you are left with. Okay, and the first thing to note is that the steady state solution, there's a phase shift compared to the driving term. Okay, the driving is of course applied with frequency, has frequency omega t, so you have the driving term over here is sine omega t, but the response has a phase shift. Okay, right, so that's physically what phi signifies. Okay, you can also look at the amplitude. Okay, so you can see that if damping is very large, as in B is very large, then the amplitude of your steady state solution is going to be small, exactly what you expect. The bigger the amplitude of your driving, as in the bigger the value of A, the bigger the magnitude of Yp, which makes sense as well. Okay, but the magnitude of Yp also depends on the frequencies. Okay, now there are two questions that you ask over here. Okay, as in you want to maximize Yp, and both are actually referred to as resonance scenarios. Okay, so the first is the case in which you hold omega fixed, and you need to find out omega naught such that Yp, the amplitude of Yp is maximum. Okay, right, so omega is fixed and you are varying over omega naught. Okay, right, so for example in a RLC circuit, omega would be the frequency of your AC source, and omega naught you can vary by changing your, say for example, the value of your capacitor. Okay, so you can use a variable capacitor to tune the value of omega naught, right? That's essentially what you are doing in a radio anyway. Okay, so let's see then what happens. Okay, so just writing it out again, just looking at this now, Yp, you have from this that if omega, what value of omega naught should I choose such that I get maximum for this thing. Okay, so essentially I need to find out the maximum, I need to minimize the denominator. I cannot touch omega because omega is fixed. Okay, so I cannot touch this term over here, I can only touch this term. To minimize this, of course, because there is a whole square outside, the minimum of this is only obtained when omega naught is equal to omega. That's my resonance condition. Okay, If you want, you can rigorously find out the minimum value, okay, by differentiating, okay, but it's obvious in this case, right? Okay, if omega is on the other hand, another question we can ask is, suppose omega naught is fixed and we are finding out the value of omega such that the magnitude of ip, the amplitude of ip is maximum, okay. So now that's a more complicated question, okay. So essentially what we are trying to do is to maximize this thing, okay. To maximize this thing, of course, I need to minimize the denominator, okay. To minimize the denominator, I need to minimize essentially this thing in the square root. So actually I can let's define a new function, say capital X as omega naught square minus omega square, right? And I need to minimize capital X to minimize with respect to omega, okay, so because I'm holding omega not fixed. So this thing is equal to square minus omega square, and then you have minus 2 omega plus 8 b square omega, okay, and this of course has to be equal to set to 0. Of course you have to check that this is indeed a minimum, okay, but it turns out it is, okay. So this thing is then, this implies then you have minus 4 omega naught square omega, right, and then you have plus, right, 4 omega square omega cube actually, okay, plus 8 b square omega is equal to 0, right. That's what I am getting, okay. And then I can remove omega is equal to 0, right. So this goes away and this becomes a square, okay. Oops, this becomes a square, and then I can divide by 4, so I'll have minus omega naught square plus omega square plus 2 b square is equal to 0, okay. So in other words, omega square will be equal to omega naught square minus 2b square, right, okay. So this is my resonance condition. If omega naught is fixed, okay, right, fine. So much for the driven harmonic oscillator. Of course, you will also be saying that what happens if my right hand side, the non-homogeneous term, is some other function, say some polynomial. What do I do then, okay? Or if it's some polynomial multiplied by an exponential function, okay, or even something more complicated. Well, of course, you have all these different cases, and you have different trial functions to deal with those cases, okay. So they always some undetermined constants in the trial function, and then by substituting the trial function into the differential equation, you figure out the values of those constants, okay. And okay, so you can read more about that in chapter 8 of Boas, okay. I think it's section 6, okay, to see what happens if the non-homogeneous term is a polynomial and so on, okay, right. Of course, I don't think really that I should be covering that, okay. I've given you the basic spirit of the method, okay, and you can adapt your guest function to some other kind of non-homogeneous functions, okay. There is another method called the variation of parameters that allows you to find out the particular integral no matter what the non-homogeneous term is, okay. And it also works when the coefficients in your differential equation are not constants, okay. It can also work for that, okay. So I'll cover that later, okay, once we come to differential equations with non-constant coefficients, okay. That's called variation of parameters, okay. But for now I want to make one important point which will also motivate Fourier series later on. Okay, so the important point is that suppose you have a differential equation that looks like this. You have some linear order, okay, which contains a double derivative, for example, x on y. So you have a second order non-homogeneous linear equation, but instead of simply f of x over here, I also have plus g of x. So the non-homogeneous term is a term of two functions. Okay, so in other words, you can also say that there are two driving terms. Okay, right? So how do I solve this then? So the idea over to solve this is once again that you first of all find the solution to the homogeneous equation. So you have first of all find yc. Okay, once you have found yc, you find yp1, where yp1 is defined in this way. Okay, right? So you only consider the first non-homogeneous thing on the right hand side. Okay, then you solve this, you solve for yp2. Okay, so you now consider that you forget about one of the homogeneous terms, you only consider the second one now. Okay, and then it's easy to check that the linear operator acting on this thing will, of course, because this is a linear operator, will give you, right? And this thing is by the way that we have found yc, yp1 and yp2 simply equal to, okay, in other words, and this is of course is equal to f of x plus g of x. In other words, this yc plus yp1 plus yp2 is a solution to your differential equation where the non-homogeneous term is a sum of two functions. Okay, so if you have a more complicated non-homogeneous term, okay, but you can write the complicated non-homogeneous term as a sum of functions, okay, whose particular integrals you know how to find, then that's it, you are done. Just do them one by one. Okay, and that gives you a big motivation behind writing down a function as a Fourier series. So let me tell you what a Fourier series is. Okay. I won't give you too much mathematics, of course, we'll do this later on. Okay, so Fourier series, if you have a periodic function, so if you have, as in your driving term is periodic, okay, no matter, it can be a sine, of course, is periodic, a cosine is periodic, okay, but of course periodicity can be anything, okay, it can be a sawtooth wave, it can be a square wave, and so on, okay, any periodic function whatsoever. A periodic function can be written as a sum of complex exponentials, okay, as in exponentials whose exponents are imaginary. Okay, just like we wrote for the sine function, remember we wrote that as a e raised to power I omega t. Okay, so any periodic function you will write as a sum of complex exponential. Okay, and since this is sum of complex exponential, I know how to deal with each individual complex exponential. I can figure out if the driving term is any periodic function, I can figure out the particular integral for that. Okay, provided I can write down the Fourier series for that periodic function, and I can do that. Okay, right? Okay, so that gives you a big motivation behind Fourier series. Okay, so there's still lots of topics in differential equation we'll cover later on once we have more tools. Okay, but I think that's it for now, and you should easily be able to do the assignment 4 now. Okay, right, let me know if you have any problems via email. Okay, I'll also intend to meet you face to face next week. Okay, so best of luck.